Thank you for joining this lesson. We're going to continue with the fluid flow. Therefore, I'm going to define volume flux, which is also called a flow rate, and also mass flux. And finally, I'll be defining the equation of continuity. Let's begin with volume flux. Generally, we should know that a volume flux is the volume of a fluid passing through a given section of a tube of flow per unit time. Therefore, mathematically, we can say that volume flux equals to volume of a fluid passing through a given section divided by time. And that means the SI unit of volume flux will be cubic meter per second, which can be abbreviated as cubic meter per second. These are called derived units because volume is in cubic meters and time is in seconds. Then we can also consider a certain tube of flow here, which is having a section B. Section B whose length is distance B. Then we can check how volume flux can be deduced from such a tube. So if the volume at that region equals to this, and the average cross-section area is also let to be this one, and the distance covered by the fluid in the direction of the flow within time t equals to distance d, then the volume flux through that region will be given by volume flux, which is also called flow rate, is given by volume out of time. Therefore, volume out of time, the formula is there. Then now we should know that volume mathematically is given by cross-section area multiplied by length. Therefore, when we take cross-section area of that tube of flow times the length within region B, you get this. That is the volume. Therefore, in the formula now, volume can get substituted by this. And so we'll say distance times cross-section area out of time, we'll get volume flux. But now mathematically, when this distance and time, distance over time, this one gives us velocity. Therefore, because that is velocity, then we can say that volume flux equals to velocity times cross-section area within a given area. Therefore, volume flux mathematically can be equated to cross-section area of the tube of flow times velocity within the given region. We can talk of mass flux, and this is the mass of a fluid that flows through a given section of a tube of flow per unit time. Therefore, mass per unit time. So we can say generally, in measurement 1, we say that mass equals to volume multiplied by density. So, in our formula for mass flux, now we will say, which is mass per unit time. Instead of mass per unit time, we can have density times volume per unit time. But again, volume per unit time, this part of the formula now becomes volume flux. Therefore, we can say mass flux equals to density multiplied by volume flux multiplied by volume flux multiplied by volume flux, which is volume per unit time. Therefore, because again we know the formula for volume flux, then we will need density multiplied by, instead of volume flux, we can use velocity and cross-section area. Therefore, mass flux is usually given by density times the velocity of the fluid multiplied by cross-section area of the tube of flow. So that is what we call a mass flux. Again, mass flux units will be given by, because it is mass per unit time, the SI unit will be kilogram per second. Kilogram per second. We can also derive the same units actually from the final formula here, which says that mass flux equals to density times velocity times cross-section area. So density is in kilograms per meter cubed. Velocity is in meters squared per unit time, so per second. Then we have cross-section area, which is meters squared. Remember, this is meters per second, sorry, not squared. Meters per second for velocity. Therefore, in the numerator, meters per second and meters becomes cubed. Therefore, meters and meters squared will cancel with meters cubed. Then we remain with kilogram per second. So kilogram per second can also be given as a derived unit. We can talk about now the equation of continuity, in which case we say that there are some assumptions which are taken into account during the derivation of this formula or this equation. The assumptions made are three. The fluid is flowing steadily, that is, it has streamlined flow. Again, the fluid is incompressible, and the fluid is non-viscous. Non-viscous, incompressible, and having a streamlined flow, or rather flowing steadily, because another name of a steady flow is a streamlined flow. Deriving the equation of continuity now. Consider the tube of flow below with changing cross-section areas. Actually, the diagram is not here, but I'm going to bring it. So we can talk of a tube of flow which is like this. Then so we can have cross-section area, area 1, and within the other end, cross-section area 2. So section 1 has this area, while section 2 has area 2. Then we are saying velocity of the fluid in section 1. So velocity here is v1, while in section 2 it is v2 at that end. We also told that the volume of fluid through section 1 per unit time is equal to the volume through section 2 per unit time. In other words, flow rate, which is equal to volume flux, is a constant for every tube of flow. Therefore, in this case, we will say that the volume flux at section 1 equals to volume flux at section 2. Therefore, volume flux, which is given by cross-section area multiplied by velocity, will be equal to cross-section area 2 multiplied by velocity at that point. In other words, we are saying volume flux is a constant. It is a constant. So volume flux being a constant means, you know, at the first section here, cross-section area is very small. That means volume velocity is going to be very high. Therefore, cross-section area is less, but volume is high. Velocity, that is, sorry, velocity is high. The other side, whereby cross-section area now becomes great, now the velocity has to decrease in such a way that proportionally it's going to be uniform. So volume flux becomes uniform, because even if cross-section area changes, the velocity with which the fluid is passing at will increase or decrease proportionally to make sure that volume flux remains a constant. So we are saying that volume flux in section 1 equals to volume flux in section 2. Therefore, this is it. This is it. Cross-section area times velocity equals to a constant. So the equation up there is called the equation of continuity, which is also called the flow rate equation. The flow rate equation. So that being the equation, we have several examples. Like in the first case here, we are told that water flows through a horizontal pipe at a rate of 1.00 meters cubed per minute. Determine the volume, determine the velocity of water at a point where the diameter of the pipe is 1 centimeter. It's 1 centimeter. Therefore, what we do is that we say that the equation of flow rate, which is uniform, so we say flow rate, which is given by area and velocity, should be equal to cross-section area and velocity of the other side. For the first side, instead of using the formula, we will use the provided cross-section, the provided volume flux already. So the volume flux is already given as a quantity, which is 1 per unit time, so over 60, because this is per minute. Then when we go to the other side now, we will have to get cross-section area, which will be pi r squared. The radius is 1.0 times 10 to the power of negative 2 squared. That is cross-section area times their known velocity. And when we divide this product through to remain with v, you are going to get the velocity in that other region. This is going to be 212.18 meters per second. The question can even be drawn like in the second case here. The figure below, there is cross-section area here, there is a length, there is also cross-section area on the other side. So you can follow through with the working until you get the value of velocity on that other side and also velocity on the second side, which is the wider side. After that, you can follow through with these questions here. Before next time we come to discuss the Bernoulli's effect, you can check a few examples here, which I expect you to have already solved. Thank you so much for following. Subscribe and share.